Hello, everyone. Thank you so much for joining our webinar today. I'm excited to have Wilfredo Ocasio and Shirin Abd here with me today hosting the webinar. I am Katie Breinig, and I will be moderating today's session. Before we begin, I will let you know a little bit about how this webinar will run. Today's webinar is being recorded, and the recording and the slides will be available to you within 3 business days. A short Q&A will follow the presentation to answer viewer-submitted questions. During the webinar, you can submit questions you have using the sidebar menu. Select the Questions tab, type your question in, then hit Enter on your keyboard. Remember, you can submit questions throughout the webinar. That concludes my brief introduction today. Wilfredo, I will now pass the webinar off to you. You may begin your presentation.
Thank you, Katie, and welcome to all of you joining our webinar today on validation of thermal process applied to low water activity foods. Today, we're going to start by providing some definitions of the concept of validation and comparing it to verification and the differences between these two concepts. Then we'll jump into why is it that low water activity foods are an important consideration in terms of microbial risk. And then my colleague, Ms. Shirin Abd, will talk to you about the actual validation study. She has way over a decade of experience doing this type of work. So she is a source of much important information. So start by talking about this concept of validation and verification. So from the food safety modernization standpoint regulation, the definition of validation is as follows: obtaining and evaluating scientific and technical evidence that a control measure, combination of control measures, or the food safety plan as a whole, when properly implemented, is capable of effectively controlling the identified hazards. And that's distinguishable of the concept of verification, which is the application of methods, procedure, tests, and other evaluations, in addition to monitoring, to determine whether a control measure or combination of control measures is or has been operated as intended, and to establish the validity of the food safety plan. Now, that is all from the standpoint of the regulatory definitions. From a layman's standpoint, the way I look at it, in my own words, is that validation is about answering the question: are the control measures the right ones? Will they work? This is something that you do prior to startup to make sure that the control measures that you have in place will work as intended. Monitoring, on the other hand, is about answering the question: are you staying within the critical limits? This is something that you do in real time during the production, and it's not oftentimes a continuous update. It could be somewhat periodical monitoring, but is an ongoing activity during operation. Verification, on the other hand, is about: do you say what you do? Do you do what you say? And it's something that you do periodically to assure that the system is under control. So this could be in the form of finished product testing or something along those lines to verify that the process is under control. So who is responsible for the validation activities? So from a Food Safety Modernization Act preventive control rule, that responsibility falls on the shoulders of the preventive control qualified individual, who by regulation must oversee the validation of preventive controls. If you look at ICMSF, Microorganisms in Foods number 8, that responsibility is given to a team of experts. And I like this definition because I always think about these operations as being complex and requiring a number of different expertise. And in ICMSF, they mentioned that this is a team of experts are required for system validation because of the many skills required, such as engineering, microbiology, physical chemistry, etc. And from a gathering from the food industry that we put together in 2013 and published a paper in Food Protection Trends. The establishment of food safety functions, including validation, again, is a team effort. So when to validate? When do we need to do this? Going back to the rule of preventive controls, validation is required prior to implementation of a control measure or when changes occur that necessitate revalidation. So initial validation is required prior to implementation or when necessary during the first 90 days of production. A food safety plan must be reanalyzed every 3 years, but keep in mind that this reanalysis or reassessment of the food safety plan is not revalidation. However, the reanalysis may reveal the need to revalidate. It's really important to have a good management of change program in place, normally referred to as MOC. This oftentimes reveals the need for revalidation when it's necessary. What are some potential triggers for revalidation after the initial validation is completed? Well, there could be new pathogen information or higher risks associated with a given product. Monitoring or verification may show indications that the system is not working as intended, or perhaps the concept behind the control measure is not working as intended. There may be changes in the ingredient microbial load that require revalidation. There could be changes in the product formulation, on the product intrinsic parameters such as pH, water activity, etc., or the processing parameters. You may be doing something different. You may be lowering a temperature, or realize that a temperature that you have assigned as a critical limit is too high, and the product or the system cannot take it, so it requires validation at a lower temperature. The storage conditions for the product might have changed. The product category might have been linked to an outbreak, or they could have been regulatory agency alerts. There could be new information in the scientific literature or consumer complaints, all of which may be potential triggers for revalidation. So let's talk about this category specifically of low water activity foods. First of all, let's just define it to make sure that we're all in the same wavelength as far as what is a low water activity foods, and this is simply defined by FDA as foods with a water activity of 0.85 or below. Some examples of low water activity foods, it's a wide variety, includes dry fruits and vegetables, cereals, confections, peanut butter, and other nut butters, dry protein powders, egg powders, teas, herbs, spices, condiments, flour, etc. And in terms of processes, there's a wide variety of processes applied to low water activity foods, including drying, like for example, drying of pasta, extrusion in dry pet foods, dry roasting, pasteurization using superheated steam, baking, processes prior to drying, as well as vacuum, microwave, radio frequency, etc. So one thing to keep in mind, though, is that a lot of this legacy equipment that is used, for example, in the drying of pasta or extrusion processes, etc., using legacy equipment are not designed as pasteurization systems. They were designed for an intended purpose of drying the food and having the right consistency or the right texture, etc. So sometimes as we go through these validations, it is difficult to make sure that we have all the bells and whistles in place relative to the equipment that you need to have in order to have a proper control measure. So why are we so concerned about low moisture foods? Well, a quick look at the number of outbreaks in the last decade plus, you can see that there's been quite a few outbreaks related to low water activity foods, mostly involving Salmonella, but you can also see that E. coli 0157A7, and in one case, E. coli 10, or a couple of cases, other E. coli STCs have also been implicated, as well as Chronobacter. So pathogens will not grow in low moisture foods. So this drives the misconception of a low microbial risk relative to these particular products. But the reality is that pathogens may survive for extended periods of time in these products at low moisture levels, and that the infectious dose for some of these organisms is extremely low, and therefore illness can be caused even in the absence of growth. Another aspect that complicates this category is the fact that microorganisms such as Salmonella and E. coli display a much higher thermal resistance at the low water activity levels as compared to high moisture, high water activity levels. And finally, like I mentioned before, Salmonella is the most prevalent, but there's been other organisms implicated as well in outbreaks related to this category. Just a quick site here and a publication by one of our authored by one of our research microbiologists a few years ago. It just illustrates how long these pathogens may survive in low water activity environments. As you can see here, we're talking about well over a year survival for Salmonella, and a very low sustained survival for E. coli 0157A7 as well. So with that, I'm going to pass the baton to my colleague Shireen Abb to talk about the process of validation.
Thank you, Wilfredo. In this part of the webinar, we talk about the process validation study and how to do a process validation study in plant. Let's first review what is the goal of the validation study. The goal of the validation study is to determine if a given process applied to a given product is sufficient to eliminate and reduce the risk associated with the product. This can be accomplished by support from the scientific publication, predictive mathematical models, or process validation study using a surrogate. Our main focus today will be on the process validation study using surrogate organisms. Next slide, please. To conduct a validation study, Eurofins proposed a multi-phases approaches. In phase 1, which is the product process assessment, phase 2 is surrogate evaluation, phase 3 is in-process validation study, which is the main part of the project, and finally, interpretation of the data and review the final reports. Now we have a couple of poll questions that I would ask Kate Lee, please present those questions.
All right, our first poll question here I'm gonna launch. Our first poll question is, do you currently have a product or products you know will require a validation study to comply with FSMA? Please just take a moment to answer yes or no. I'll give everyone about 45 seconds here, and then I will close the poll and pass it back over to Shireen with the results. All right, about 10 more seconds here, everyone. All right, perfect. So about 54% here said yes and 46% said no. Our second poll question here, I'm going to launch. Our second poll question here is, do you use third-party laboratories to conduct validations on site? Please take another 45 seconds here to answer yes or no. Alrighty, about 10 more seconds here. All right, perfect. It looks like about 38% said yes and 62% said no. I will pass it back over to you, Shirin.
Thank you, Katie. Can we please have the next slide?
The news in the next slide is showing us slide number 16. Apologize for the difficulty. Are you not seeing the slides?
I cannot. I'm sorry. I still see the full question.
Katie, are you able to see the slides?
I am not able to see the slides either. I'm not sure what's going on with the poll questions here.
Wilfredo, if you want to try sharing out again, I know sometimes the polling question does show, so you might have to just share out again.
Yeah.
All right. Yes, we're back to the slides now. Thank you.
Thank you.
Apologize.
Okay, here is the multi-phases project, and we will start with phase 1, which is the product and process assessment. In phase 1 of the project, first we would like to understand the regulatory requirements specific for a product and process, and also set the performance criteria. For example, the goal of this study is to achieve 5-log reduction of Salmonella in a product exposed to a process. That is the goal of the experiment and the objective of the study. We gather information about the product and process to understand the whole picture about the validation study. About the process, we would like to know information about the equipment, the manner of the heat application, temperature and time, and that refers to the temperature of the product, not necessarily the setting temperature of the unit. About the capacity of the unit, for example, if it's a dryer, the depth and distribution of the product on the conveying belts, and other extrinsic property of the process, such as relative humidity and airflow. Also, it's very important to understand the product as far as the intrinsic property, such as pH, water activity, moisture, fat, solid. All of these parameters may affect the resistance of the organism in the product, and also the physical property of the product, such as piece size, shape, surface structure, and surface area. When we gather the information and we understand the product and process that have been considered for the in-process validation study, we review the scientific literature to understand the impact of product and process property on the bacterial survival. If possible, we select the worst case scenario product for the next phase of the project. For example, based on the water activity of the product, the most conservative water activity, and also intrinsic and physical property of the product. Also, what is the worst case scenario condition for the processing equipment? It's important to identify the target organism for a process validation project. The target organism can be selected based on the food safety plan, and also it's very important to look at the past outbreak for a similar product and ingredient. As Dr. Ocasio mentioned, the target organism and outbreak associated with low water activity product could be very different organisms such as Salmonella or pathogenic E. coli or Chronobacter sakazaki. Once the target organism is selected, the implant validation study needs to be done. Now we are wrapping up phase 1. We understand the product, we selected the worst case product if possible, we know about the process, and we selected the target organism. Of course, target organism cannot be taken to the plant for the implant validation study. A surrogate organism needs to be evaluated for implant validation study. Characteristic of the potential surrogate organism is they must be non-pathogenic organism and demonstrate similar or greater resistance as compared to the target organism in the specific food, considering the process as well. The organism needs to be stable, easy to grow into high level, and easily differentiated from the background microorganism that may present in the product. The most common surrogate organism for Salmonella in low water activity food is Enterococcus faecium. This organism has been extensively studied by Almond Board of California and originally was identified as a thermal surrogate for Salmonella on almond exposed to dry heat. Enterococcus was one example of the surrogate organism for low water activity product. In the reference that you see on your screen, which is a review paper, a comprehensive list of surrogate organisms provided in this paper. Pages of reports listed the surrogate organism. The message here is when we are looking at the surrogate organism, not only we have to look at the pathogen, we need to consider the product and process. For example, Pediococcus acidolacticea is a surrogate organism for E. coli 0157H7 for a commercial drying process of the beef jerky. Again, here it's emphasizing that pathogen organism, product, and process, all three categories needs to be considered when we are evaluating an appropriateness of a surrogate for implant validation study. Next, please. More and more information are accumulating about the appropriateness of the Enterococcus faecium as a surrogate organism for a thermal validation study of the low moisture food. Here is in the most recent publication in the Journal of Food Protection in June 2022. A group of scientists evaluated the appropriateness of surrogate as a surrogate for various low water activity products, such as non-fat dry milk powder, peanut butter, almond meal, wheat flour, ground black pepper, and date paste. The result of this study indicated that Enterococcus is more resistant than Salmonella in the tested product. Therefore, it is appropriate to be used for validation of the thermal processing of the multiple low moisture products. Again, this is a common surrogate for low moisture product exposed to the thermal processes. However, it doesn't fit all the time for all products. And there is a statement in the abstract of this paper that says, however, the product composition should always be considered making that decision if the Enterococcus is appropriate surrogate for Salmonella to be used in the implant validation study. If the information available in the literature, we refer to the literature and then we use an appropriate surrogate for the implant validation study. But that's not always the case. If the product is specific very specific, and that information is not available in the literature, Eurofins can conduct an in-laboratory study to evaluate the appropriateness of the surrogate. Here is one example. It was a product, a low water activity product, and the two groups of target pathogen were selected as a target organism for this product and process validation study, which is E. coli 0157H7 and Salmonella. The appropriateness of the surrogate was studied here. The product was separately inoculated with Enterococcus, E. coli, and Salmonella, and exposed to the various thermal treatment. For example, 150 for 20 and 40 minutes, 160 for 5 and 10 minutes, and the survival of each organism evaluated before and after the process. The result of the experiment shown in this graph. On the y-axis, you see the log reduction, and in the x-axis is the thermal processes applied to the product. The shorter the bar is, means less log reduction, therefore the organism is more resistant. Here, the orange bars, in all cases, are shorter than other two bars. That means Enterococcus is more resistant than E. coli and Salmonella. Therefore, the result of this experiment shows this organism, Enterococcus, is an appropriate surrogate to be used for implant validation study in this specific product. Let's wrap up our phase 1 and phase 2. We looked at the product and process. We selected the worst case product, if possible. Now, we identified the target organism. We selected an appropriate surrogate organism based on the information available in the literature or based on the data generated in the lab. Now we are ready to conduct the implant validation study. Before I get to that, I would like to bring the point about the temperature mapping. If possible, it is highly recommended to assess and map out the temperature distribution achieved in the unit operation to identify the cold spot. When you identify the cold spot of a process, basically you are identifying the worst case location, the cold spot of the process, and you would like to cover that by the implant validation study, by the surrogate validation study. In the next slide, we will cover that again. The temperature mapping can be done by placing the probe in different locations of the processes and then run the process and basically take a look at the temperature mapping and see what was the cold spot of the process. If possible, that is recommended. However, in some processes, temperature mapping is not possible. For example, in the extrusion process, you cannot run a probe to the extrusion process and study the product temperature during the extrusion process. We are moving forward with the implant validation study. The product, worst case product, needs to be inoculated with a surrogate organism. The inoculation should be done in a way that does not change the intrinsic property of the product. If the inoculum added to the product is a liquid inoculum and may change the water activity of the product needs to be dried to the original water activity after the inoculation process before it will be used for implant validation study. Inoculum level should have a high starting level to be able to quantify, for example, a minimum 5 log reduction. Inoculum should be stable in the product. And a very important point here for implant validation study is how to introduce the inoculated product through the process. In an ideal case, the whole batch of product will be inoculated. For example, in the picture that you see on the right side of your screen, this is a dry roaster for sesame seed. If the capacity of this dryer, for example, is 50 pounds, in an ideal case, you would inoculate the whole 50 pounds of product and run it to the process, collect some sample before and after. That is the way it's the introduction of the inoculated sample will be done through the system. But this is not feasible all the time for different reasons. For example, if the capacity of the unit is large and the whole batch of product cannot be inoculated. Another way of the introduction of the inoculated product to the system, if the whole batch inoculation is not a choice, part of the sample can be inoculated and basically marked with dye and run it to the process. That is an example that you see in the middle picture here. The portion of the sample was inoculated and then dyed using the red color and then processed it to the sample, and sample were collected at the end of the process. Another way of the introduction of the inoculated product to the process, which might not be the ideal case, but still it can be done if other option doesn't work, is contain the inoculated sample in the mesh bags and place the mesh bag into the process and retrieve them at the end of the process. Now we have done our inoculated sample ready. We developed a protocol for the on-site validation study. We defined the worst case process parameters. We have a plan how to place the inoculated sample into the process. Here again, a couple of other examples of the on-site validation study. On top screen, you see the whole batch of product was inoculated, placed in the tray, and then also a thermocouple was placed in the different location on the tray. On the other picture that you see here, the inoculated seed was placed into a mesh bag, and mesh bag was inserted into a larger bag that contained the product, the bulk of the product, and then that bag was placed into the pallets of product and processed by the steam sterilization process. It's also very important to collect all of the test parameters data during the implant validation study and include appropriate positive and negative control sample in the process. The last phase of the in-process validation study is collecting the sample after the process and pack them, including the negative and positive control sample, and ship them to a facility, to a laboratory for the enumeration process. It's very important to avoid cross-contamination of the sample during the collection and also the shipment. Sample should be kept cold during transportation and needs to be enumerated as soon as it reaches the destination, the laboratory. During the enumeration process, the use of selective media needs to be avoided to consider the recovery of injured cell. Also, there are some challenges for the enumeration of the inoculated sample post-process. The background microflora of the organism may interfere with the count of the surrogate organism. If that is the case, confirmation of the surrogate organism colonies on the plate needs to be done. Okay, we're done with the main part of the project, phases 1, 2, 3. The surrogate was evaluated by the process, and the log reduction now is the time to analyze the data and report the data. The log reduction calculation, it's a simple calculation. Basically, we know what the level of the surrogate was in the inoculated sample prior to the process. We enumerate the sample after the process, and we can simply calculate the log reduction here. Based on the result of phase 2, which we evaluated the appropriateness of the surrogate, the log reduction of the pathogenic organism by the process can be determined. Let's bring an example here. If we run a surrogate organism through a process, when we achieve greater than 5 log reduction of the surrogate organism by the process, and if we evaluated the surrogate, the thermal resistance of the surrogate versus the target organism, And the result of that phase, that surrogate is more resistant than the target organism. Therefore, we can draw the conclusion that the dryer or the unit operation was effective to deliver 5-log reduction of the pathogenic target organism as well. Here, as the last point, I would like again to emphasize the most common performance criteria for the validation on the low water activity food processes are 5-log reduction of Salmonella. However, it depends on the risk assessment for the product and process. Other organism may be identified as a target organism for these type of projects. Process lethality calculation and final report is basically what you're gathering over the multi-phases project, and it's very important how to present this data. This is a document that will be reviewed by the regulatory agency. For example, if you have an audit. In the final report that Eurofins prepare after the process validation study, the background information will be provided in the report, why this experiment has been done, what was the performance criteria, what is the objective of the experiment. In the protocol section, all detailed information will be provided in a way that the report and the project basically can be reproduced. All of the information about the inoculation and enumeration of the sample, process description, facility address, process parameters, number of replicate sample, description of the positive and negative sample, methods for the inoculation of the sample, the introduction of the inoculated sample to the process, and recovery of the sample. Again, all the detailed information will be provided in the protocol section of the report. In the results section, pH and water activity of the sample, including negative control, positive control, and test sample, will be reported. Initial level of the surrogate organism in the inoculated sample and population level of the surrogate organism after the process for each sample will be reported, and log reduction for each sample will be calculated. In the conclusion section, the efficacy of the process on the log reduction of surrogate organism and selected target organism will be stated. And in the appendix of the report, surrogate evaluation data, temperature data, if it's collected, photos and other information will be included. There are some reports out there from the process validation studies, basically just saying the counts of the surrogate organism before and after the process. This it's not a comprehensive report that can be presented as a validation study, for example, to the regulatory agency. A process authority should be involved from step 1 of the process validation study. If you're considering to do a process validation study, basically looking at selection of the worst case product, development of the protocol for your process, the execution of the experiment, and the most important is the comprehensive report for the validation study to be issued to include all of the information that has been collected during the multi-phases project. Thank you.
All right. Thank you for the presentation. We will now move on to a short Q&A. Feel free to continue to submit questions during this session. If we do not address your question that you have asked during the live presentation, we will follow up with you in an offline email. Our first question here is, I have a large number of similar low moisture products. Do I have to conduct challenge studies for all of them?
No, not necessarily. What's the way that we can help if you have a number of products? Basically, as I mentioned in the product process assessment, we can look at the information, intrinsic and extrinsic property of the product, and categorize them. And then, if possible, select the worst case scenario from each category to be used for the on-site validation study.
Thank you, Shirin. Our second question here is a 5-log reduction always needed for a successful validation?
Not if the performance criteria is not defined for your specific product and process, 5-log reduction is the most common performance criteria. However, if you have done the risk assessment for your product and process, and I can bring an example. Almond Board of California collected data, extensive data over 5 years, and evaluated the risk associated with their product. And they were able to justify the full log reduction as performance criteria for the process validation study. Again, if data and risk assessment is not available specific to your product and process, 5-log reduction is a common performance criteria. But if you have done the risk assessment and you have enough data to justify for lower log reduction, that can be considered.
Thank you again, Shirin. Our third question here is microbial challenge validation required by the FDA?
Thank you, Shirin. So, not necessarily if you have, for example, clear understanding of the resistance of the pathogen in your particular product and process, you may be able to collect temperature data if, again, that is available, and correlate that temperature data to the kill of the given microorganism. Unfortunately, in most cases, we're talking about these legacy systems, there's not enough information that you can collect on the temperature of the product, and there may be other variables involved as the product is changing, moisture levels as it goes through the process. The relative humidity of the chamber may change, things that are difficult to predict, and hence the necessity for the surrogate and microbial validation. But is it an absolute requirement? No, it would have to be looked at on a case-by-case basis.
Thank you, Wilfredo. Another question we have here is, can I use information available in the scientific literature instead of conducting a challenge study?
Again, yes, that is connected to the previous answer. So if there is information in the scientific literature that can be applied to your product and process specifically, you may be able to use that information. Again, the preventive control rule opens the door to validation taking different shapes. It could be information in the scientific literature. It could be done via information from trade association, industry standards, etc., as long as it's scientifically valid. Again, the challenge, no pun intended, is it resides on the design of the systems and the complexity of the product as it changes through the process.
Thank you, Wilfredo. Another question we have here is, water activity changes throughout many of these processes. What water activity do you use to evaluate your surrogate?
I can take that question. In the ideal case, you wanted to evaluate the surrogates in different matrix. For example, if the water activity is changing during the process, you want to evaluate the surrogate of the product before the process, in the middle, of the process, as the end of the process. However, we understand that is not feasible in many cases due to the limitation of sources and timing. Therefore, the worst case product, which is the finished product, will be used for this type of evaluation. Again, there might be some question and concern about, the finished product. It's a worst case scenario product, and we may set the criteria for, not the optimum condition. and set the criteria for possible failure in this case. In the recent meeting at IFP this year, 2022, Dr. Nate Anderson from FDA briefly mentioned that this scenario needs to be evaluated case by case. In some cases, it would be possible to use the intermediate product for the surrogate evaluation. Again, each case needs to be considered and needs to be studied very carefully and select an appropriate surrogate for the evaluation.
Thank you. Our next question here is Salmonella always the target pathogen?
It is the common pathogen organism. Over years and years, there was concern about Salmonella and high resistance of Salmonella in a low moisture product. However, it's not the only target organism. In a slide that Dr. Ocasio presented, you have seen, other organism was associated with the outbreak of low moisture products, such as pathogenic E. coli, and in a recent outbreak of Chronobacter sakazaki. Again, this is the common target organism, but not necessarily the only target organism. For the selection of the target organism, we need to review your product and process, and basically based on the food safety plan, select the target organism and also consider the risk associated with your product based on the previous outbreak with a similar product and ingredients.
Thank you, Shirin. Our last question that we're going to take here is, what do you do if the surrogate evaluation shows that the target pathogen is more resistant than the surrogate organism?
So it depends on the magnitude of the difference, right? So there might be some rare situations where the pathogen is slightly higher in resistance than the surrogate organism. If you're able to quantify that difference, you may be able to adjust the inoculum level up higher to compensate for the lower difference. But that's kind of an unusual situation. Most of the time in that type of situation, you would have to search for another surrogate organism that better matches the surrogate in question. And we've done that many times, and unfortunately that's a significant effort to go search for other potential surrogates, but they do exist, and we have been able to use other, for example, Pediococcus, for example, instead of Enterococcus faecium in some situations.
Thank you, Wilfredo. All right, that's going to wrap up our Q&A session today. Thank you again, Wilfredo and Shirin, for joining us today. I also want to thank everyone for attending today's webinar. Also, a recording of this webinar, along with a copy of the slides, will be available to you within 3 business days. Thank you for your expertise and presentation today. Thanks, everyone, for attending.
Thank you.
Have a great rest of your day.
Thank you.